Hello everyone and welcome everyone to the sixth session of our 3D Thursday webinar series. So I'm thrilled to have you all with us today as we explore the exciting world of additive manufacturing. So as many of you know, additive manufacturing or 3D printing is revolutionizing industries. So our topic for today's session is unlocking the potential of additive manufacturing in oil and gas industry. In this session, we will delve into how the oil and gas industry is evolving rapidly, with additive manufacturing playing a very crucial role in driving efficiency, reducing costs, and enhancing supply chain resilience. This webinar will explore the need for a collaborative approach with supply chain partners and transformative value of AM, highlighting its impact on part optimization, on-demand production, and sustainable operations. So let me just explain you the rules and regulations for the question and answers. So we encourage an interactive session. So please feel free to ask questions. A dedicated question and answer segment will take place at the end of this presentation. But during any point of the presentation, you can submit your questions through the chat box feature. So to ensure everyone has a chance to participate and get the answers for all your questions, we will be addressing a few similar questions together. So we'll address as many as time allows us. So please don't hesitate to share your thoughts. And lastly, please note that this webinar is being recorded. So by participating, you consent to the recording being shared for educational purposes. So I would like to introduce you all to our speaker today. So I'm excited to introduce our speaker for today's session, Mr. Nandakumar Thankavel, a global sourcing leader at Celeros Flow Technology. So Nandakumar Thankavel is a supply chain leader with over 25 years of experience in supplier development, quality, and new product development. So he began his career in the valve sector, moved to automotive sector, and back to the valves and pump sector, focusing on enhancing product development processes and improving supply chain operations. Over the years, Mr. Nandakumar has built expertise across a variety of industries, including automotive, energy, and manufacturing. As a global sourcing leader at Celeros Flow Technology, he is responsible for driving sourcing strategies, driving new technologies and innovation, and optimizing supplier relationships. So Mr. Nandakumar works very closely with the global teams to ensure supply chain quality and efficiency, helping them further in streamlining the operations and deliver impactful results. So let's welcome Mr. Nandakumar Thankavel as he takes us through today's presentation. Over to you, sir.
Thank you very much, Santosh. Good evening, good day, everybody. Thank you for joining this webinar. And I take this opportunity also to thank Wipro team for giving me this opportunity. So in today's webinar, we'll be quickly touching upon a successful business case, a product development case with Wipro and Celeros, where I will tell you about some of the challenges we face, some of the lessons we learned, and some of the good things that we did, etc. So this is going to be focusing on the specific business case that we are going to deal here. Okay, next slide. So the slides are, arranged in this particular agenda based, roughly on this lines. And on the right side, you can see the values of a company. So this is approximately going to take about 40 minutes, and then we'll leave it for question and answer session. Okay. Next. As part of a company culture, we start every session with a safety moment. And the safety moment for today is something that I saw or read recently. and is that says sitting is the new smoking, and it's truly a silent killer. And it also elaborates to say that sitting for long periods can cause health problems, including the big ones that are listed here. So the article also goes on to say what can we do about it. It says that take frequent breaks, and another study also promotes like walking 200 steps once in every 30 minutes, which they claim to be as good as a continuous 10,000 step walk. But in whatever it is, avoid sitting for long times, take breaks, take frequent breaks, just just walk and move your body. I think we should be, you know, not looking at the safety hazard on this. Yeah, next. As you can see, I work for Celeros Flow Technology, and this a couple of slides about introducing a company. And you can also read from the title that we are into flow control business. Our portfolio includes pumps, closures, and valves, and some of the heritage brands. Many of them are over 100 years. You can they are Clyde Union Pumps, M&J Valves, GD Engineering, but that's for the closures. Plenty Pumps, Coops Vulcan again valves, and SNN Pumps. These are some of our key brands that are under the Celeros, you know, company. We are into manufacturing, installation, maintenance, refurbishment, upgrading, decommissioning of equipments related to flow control business. And we serve industries, oil and gas, energy transition, primarily about the new forms of energy, the carbon capture technology, etc., water, nuclear, marine and defense, power, conventional power. And we plan to be carbon neutral by 2030, and close to 50% of our business is coming from aftermarket, which is a significant margin for, in share in terms of the market for any company. So I have highlighted in red because that's one of the key decision makers for us to take the steps towards additive manufacturing. Next. Quickly about the oil and gas and valves, because that's where the component that we're going to talk about lies. So in the valve side, we are in upstream, midstream, and downstream operations. We are an engineering partner for transportation, storage, refining, and processing of oil and natural gas. And again, like I mentioned before, we are into the maintenance, refurbishment, upgrading of storage and transportation infrastructure related to oil and gas. And on the valve side, there are multiple valves here. So we do control valves also for the nuclear applications, gate valves, check valves, diverter valves, do desuperheaters, direct steam conditioning valves, surgery valves, etc. And if you need more information of a company, you can go to a website and you can have this information. Next slide. So this is a quick overview of the products in terms of some photographs here. I have red boxed one particular, part, which is the trims. These trims are integral to our valves, which means that they form part of the valves actually. And we also sell them in the aftermarket. So I have highlighted that because that's going to be the point of discussion today, because one of those components is what we developed in additive manufacturing actually. Next slide. Okay. So when we started this, maybe when we started this thought process about going into the additive manufacturing. So why did we go into additive manufacturing? Why did we want a component like that? So the first thing is about the way the market is. In fact, as I mentioned to you, we have a huge demand for aftermarket, and we are into aftermarket business. So if you look at the aftermarket business, they are very specific, like it's application tailored for each and every application. The components are tailored, so it's almost like a custom made part actually. They need in very short lead time. The parts are highly engineered, and they need it at business friendly prices. Again, I'm not saying that it's the cheapest price. We needed business friendly pricing, because in aftermarket, we need to align the timing of the part in accordance to the when the the process equipments are available for the maintenance. And materials, again, we're talking about very special materials, stainless steels and Inconel. And we selected valve internal, as I showed you, the trims as a pilot for our additive manufacturing experience. Unfortunately, I cannot share the full photograph of the trim part that we made due to confidentiality. But I can tell you why we took a decision to move towards additive manufacturing of that particular part. In that particular component, we were manufacturing it in a conventional manner. And when I say conventional manner, that component had about maybe about 35 different stacks, which had a complex flow profile inside it, and that need to be put into a particular order and then joined together by spot welding and brazing, and then it needs to be heat treated. So even the machining process that I mentioned on each of these stacks, because they are very thin, is a very, very complex machining process. It's not the normal machining process that we're talking about. So as you can imagine, this for manufacture of this component, it would need multiple suppliers, multiple different kinds of supply chains, movement of the part here and there, and then we are talking about so many things that needs to put, then heat treatment, then brazing. So all of these put together made the part a very, very highly engineered complex manufacture. But what it also did is it made the lead time longer, and we were also dependent on limited suppliers for welding consumables. So all of this made us think that we should be looking at the additive manufacturing for this particular component. But there's a small note here. Our facility in the US already had a 3D printer, so they were aware of the process. They had competence about this, people who know about this process. So it was not that difficult for us to take the journey and convince people, etc. So it was like more of an ask from their side, which we implemented in India. Okay, next slide. Okay, this is the journey that we had. This is, of course, the slightly technical discussions that we had with Wipro 3D here. And there were multiple discussions that we had in person at their factory discussing about the technical requirements. And I wanted to share a couple of things that would help anybody who's interested in taking this journey. The first thing, obviously, is about a very detailed 3D model, which they can slice, which they can check, which they can use it for their processing and taking it for manufacturing as well. And I think there is a we don't need to be too much debating about what kind of model is needed. There is an ASTM standard, which is a guidance standard that's available, ASTM 52915. Probably that is one good reference you can have. You can take that as a guidance for exchange of digital information for 3D printing. The second is about surface finish. And I say here we need an agreement and a validation. And when we talk about surface finish, most of our conventional drawings have, they have listed a surface finish, which probably is not needed in many cases, or in some cases it's mandatory. So we are not sure of, because it's conventionally machined and finished, or EDM and finish. So the conventional drawing would have that particular finish. But in terms of a real functional need, that surface finish need to be revisited if that's when we move to additive manufacturing. But in our case, there was no chance of reducing or compromising on the surface finish. We needed a minimum finish because there was flow involved in those passages. So what we did was, the first thing that we did was to print a small segment, and which we can see, because after printing we will not be able to see the inside finish. So we printed a small segment, and we checked the surface finish of that particular flow areas, and then we did send it to a Houston facility, and we validated it. So what I'm saying here is there are some components where the surface finish can be improved after you make the component, but this one we cannot do anything like that. So we needed to take steps prior to build, making the component. Okay. Then it's about the deposit thickness. What we have done is there are multiple options available for 30 microns, 60 microns, etc. So it's about, we need to be talking to the supplier, which is for us Wipro 3D here, and we decided the best that would be suiting for us to move forward. And that deposit thickness is is a key factor for us in the finished component. A print angle, normally our components got printed in the 45-degree angle, and when we started, we didn't have any big challenges about it. But as we started asking for bigger parts, we found that the print angle was certainly a factor that was not allowing us to make bigger parts. So that's something that you'll have to discuss with your service provider, in this case Wipro 3D, and get their help so that they can find a different angle by doing some changes, which is a DFAM. And I think that will help us in making slightly bigger parts, better parts, quicker, with some better properties. So there is, in this process, we also understand that there is some portion of powder that is not being used. So that powder can be reused actually. So the reused powder usage percentage is something that needs to be defined and need to be controlled, which Wipro is already doing. We all are familiar with material properties because we are now either would have manufactured these part in a conventional manufacturing process using maybe a casting, or in these cases it's from a bar stock which is machined. So we are familiar with the material properties of those processes, but here we need to be careful about the material properties. So we insisted and we discussed about density, and because in the end the component should be dense enough, because this is a process which can have voids in their manufacturing process. And so density was a key factor. And again, there is an ASTM standard that's being referred here, ASTM B311. And mechanical properties, which is again, there are two standards here, which is ASTM 52921 and ASTM E8. The 52921 is about, they talk about the coordinates as to X, Y, Z, because the properties and the mechanical properties are based on direction. It changes slightly in the case of AM parts. So we need that standard to say, if you have to take how many coupons on the X direction, how many on the Y, how many of the Z direction, and to find out which direction it is, you need the 52921. And then ASTM E8 is a normal standard that we use for tensile testing. So we use the ASTM E8. We did print a dumbbell for mechanical testing along with the component. And there's a microstructure examination also can be done. So there is F3055 is an example I'm citing here, which is primarily for the nickel-based alloys. For every other grade, you have a standard for that. So this is what we used. Heat treatment, stress relief process, we need to plan that in advance because in some of these parts, heat treatments can leave some marks, can cause distortions, etc. So we need to be very clear about what kind of heat treatment, what kind of or stress relief is planned, and where, etc. So in our case, we use the vacuum-based heat treatment that really helped. But if you read the standards that are coming in the recent days, the HIP is being, you can, if you look at the standards, it will talk about different classes, and they are saying, you can stress relief and then do an HIP. And from the studies which are coming in recently, and also Wipro has confirmed that study, the material properties are, better than that of castings, and very close or equal to that for the forgings. So we are talking about metal printed parts which are having properties better than castings, and properties which are close or very close enough for the forgings actually. So so in our particular case, in our in our particular case, we had some issues with post processing. So that's the easiest thing to do is to print the part actually. So if you give a drawing to a supplier, printing the part is very easy, but post processing is the biggest challenge, especially on a component like what we are discussing here, which would have about 1,000 holes like windows around the part actually. And so we had to plan a lot. We did a lot of discussions with the Wipro team, and they were very open. They gave a lot of suggestions, and I think this is an activity that needs a lot of collaboration to be done. The particular challenges we faced were, one is on deburring. In this case, we use Inconel as a material, so deburring was a big challenge because Inconel is a very, strong material. So the burrs removal or it doesn't break or chip off easily like the other grades. So that's something that we found some innovative ways in getting this. And we must also remember that in this particular case, we cannot do blasting. Even grid blasting cannot be done because the grids can get into the flow areas and can block the flow. So we cannot do grid blasting, abrasive, tumbling, none of these we can do. We have to think about different options to deburr the part. And we also need to be sure that there is no machining chip, or we also did a grinding on this part, ID grinding. So we also wanted to be sure that there is no machining chip or grinding debris that gets into the flow area. So in this particular case, we agreed upon using a special soap which would close the holes. As I said, there are close to 1,000 different holes there, or windows, I would say, flow paths, I would say, whatever you want to take it. So the special soap was used on the inside and the outside, and during the machining process. So that soap would not prevent, it would prevent any sort of grinding wheel debris or the machining chip from getting inside the part. And soap can be easily washed off after that. So the component also went through multiple rounds of ultrasonic cleaning, hot water cleaning. So and we also had innovated some ways in which we could check if the flow was working properly. So we tried some low cost inspection methodology, trying to see if the flow, it was allowing flow from one side to the other side. So what I mean is, like, there is nothing written on your drawings and specifications. It's something that you need to be working with your supplier very closely, understanding it, and then finding out what's the best solution that's possible for these kind of requirements on our particular product. So there is a manufacturing plan, and it will talk about the machine, manufacturing control system, and the qualification procedure. Again, if any of these things change, it means that you need to be really going for a requalification or a new on a new sample to be approved. Actually, we did that, and Wipro has given us the reports for that. And inspection planning, this is a again, we need to be slightly different to the conventional inspection process, except for the except for the uh, dimensional aspect, which we can do same as the conventional process. Visual inspection is different. I mean, it's different means in a conventional process, you are able to see all the child parts, then you put all of them together, etc. Here, you will not be able to see it, so we need to have special lighting arrangements to see through inside of each and every hole. And then, so there is a lot of even the common conventional radiography inspection was not, I would say it was good, but we were able to find that there were no big, there are no voids in the component, that much we can see. But then if you take the standard strict and go and check your radiography reports, that possibly is not the best one. So there are new techniques that are coming in here, which includes the CT, which we will cover in another slide. And the end of it, we also did a flow test because this is a flow component. So we did a flow test, and we are very happy that the equipment, the component passed the flow test brilliantly. I would say it was, the parameters were very almost aligned to the theoretical curve, and in some areas where the flow is higher, it was even better than the theoretical curve. So it was a great success for us. So all the activities that we planned in the post processing about how to make sure that the windows are clean, I think that gave us a success. Next. So I think we are talking about commercial. So when we talk technical things, the next question that comes in our mind is, all this is okay, but is it commercially viable? I think the first thing we need to be looking at is the overall cost. It is not just, you cannot you cannot give a drawing to a supplier, get a quote, and then compare that quote with whatever you have manufactured conventionally. So that doesn't work. We need to look at the overall cost. Like I mentioned in the previous slides, the conventional process is a very long process which involves multiple suppliers, movement of the part in very multiple places, and and special processes in several places. And with all that, we come with two different things. One is about rejections in the process, and the second is MOQs. Because when you want to buy raw materials of that sort, you cannot buy in one and two. You need to buy about like 10 or 15 of them actually. So you need to be stocking raw materials. So there is a lot of MOQ involved into that. So we need to be looking at the overall cost. And when you look at it from an overall cost, certainly I think it makes some sense to move towards additive. And lead time, the conventional manufacturing has got a higher lead time, while additive has got a shorter lead time. Of course, when you start the process, it is the first component will take you a little bit more time, but then as you go, the time will certainly decrease. And that lead time is connected to a customer experience. A customer likes that. So I think we need to factor that. And when we have shorter lead times, especially in the aftermarket business, there is also chance for, you get a premium for that. And sustainability, as you can see, our company wants to go carbon neutral, and this is certainly one of the processes that will help us achieve that. So if you are looking at additional benefits you want commercially, I think this is not a place where you can go to a supplier and ask them a 10% discount or a 20% discount like that. It doesn't work like that. So there are some options available, like if you use a validated existing powder that the supplier has already validated. So I think that will help us in optimizing the price or reducing the price a little bit. In our case, our requirement was stainless steel, but we didn't have the equivalent or the right equivalent stainless steel with Wipro at that point of time. So we moved to Inconel. So we moved to an upper grade, which also helps us with the performance in the field for us on that particular component. So we used Inconel for us, but that was a material that Wipro had already established, and it was a well validated material for them. So we had no issues on that. And as I mentioned, we had a very strong collaboration with the entire Wipro team. Not just the 3D printing team, with the machining team, with their inspection team. We had we sat across with them, and they really worked very hard to work along and take us through all the stages on a step-by-step basis. We are now working with them on DFAM, which is designed for additive manufacturing. I think that's part of the next part of the journey for us. And once you do DFAM, and I think there you will see cost benefits coming in. So that's a stage we are now discussing with Wipro. So if you want additional cost benefits, then I think you need to be looking at some of these points, which probably can help you. Next slide. So this is about how we collaborated. So the most important point is to collaborate with your supply partner. And the first thing that comes up is about confidentiality. We need a supplier who we can trust, who we can share the entire information, because there's a lot of technology transfer happening here. When you share our drawings, when we share the highly engineered products information, so we need supplier who can keep up that. So I think that's what Wipro 3D was a great choice for us in that aspect. And we need competent people, so who can understand what our engineering says, and they can take it up from there and move forward. So we are very, happy to say that, Wipro had that team as well. And we need to what we did from our engineering team is also to help them understand what is the functional and design requirements of that particular component. So otherwise many things would be assumed by the supplier for when they make the process, etc. But when you pass on the information about functional and the design requirements for these components, what happens is you will see that supplier will be able to give some solutions for us, and which certainly helps us moving forward. And DFM proposals by supplier, we spoke about this. And once you communicate your requirements, they will be able to give you something which which will not affect your design intent. But there is also one more thing. There are some patented, I would say, profiles in additive manufacturing. So we also need to be sure that our supplier is not violating any of those patents which have been patented by somebody else. So that's very important here. And again, when we collaborate with our suppliers, we there are some multiple things that we need to be changing in our side. For example, if we have a conventional inspection process, we cannot go and use the same yardstick and go to additive printing suppliers and say, by the way, this is like this, we need a report like this, we need something like this. So that's something that that certainly will not work. We need to find ways to collaborate, innovate with the supplier, find out what we can do. For example, in this particular case, of course, because of the thickness, we were not able to do the CT based inspection, but that's an option that's available. And new technologies are evolving, and it's called the real-time flaw detection. So you can identify if there's a flaw in the component even during printing of the component. We also need to be looking at adjusting or changing the purchase specifications in our organizations, because if you cut a purchase order with conventional thinking, and then the part gets into manufacturing, and when it gets back to the plant, or when it gets back to the inspection team who will be locally available, there's a lot of discussion that happens. This is not this one, this doesn't work, this doesn't. The supplier will come back and say, oh, by the way, for this process we cannot do this. So we certainly need to be looking at changing some of the purchase specifications. Like I mentioned, we had some prior experience on these things. So in our case, most of these things were handled, but some of them certainly need to be discussed. So we had discussions with our supplier, which is Wipro 3D, and we had some great success in that as well. And supplier, we also took the supplier ideas for AM in some cases. In some cases, what we have done is, like, when we told them that this component is getting welded to another component which comes down the line, then Wipro team told us that if you can share those drawings, we can find out a way in which we can blend together, or we can print these components together, so that you can make, instead of having a double part, we can have single part. And what it also does is we can able to do some customizing for our customers, and so we don't need to invest on tooling or anything like that. So we can customize and provide exact solutions instead of selecting something which is over designed for that particular customer. So so we had that kind of discussions with Wipro as well, and we are looking forward for those opportunities to move forward. Next slide. So I think this is a key slide because this is something where the question that's being asked is, machines are available, products are being made, but why is that in oil and gas not every component can be printed? Okay, so because I'm we are talking about so many things. There are so many printers available in the market, so many things are evolved, and you can see that aerospace is using a lot of additive printed parts, and you can there are medical sciences using additive printed parts. But in the oil and gas industry, we still are not seeing that kind of I would say a presence of additive printed parts actually. But I would say technology is evolving. I know that, but uh, the most important thing that stops is that the availability of these standards. Because in oil and gas, we're talking about pressure parts, and there are two different kinds: pressure containing and pressure controlling, and they are all governed under the pressure equipment standards. So these are not similar to the other industry parts, which probably are structural. Some of them may be rotating, and all of them may be very, very critical. But the pressure application of these parts in the oil and gas industry make it completely different to the other industries. So the kind of speed in which this is getting into the oil and gas industry was slow, but I think a lot of things has happened. So one of the key standards that has been introduced that really helped is APA 20S. It talks about the qualification of manufacturing processes for oil and gas. There are three different technologies: PBF, DED, and BJT. These are the approved processes. Using this, it says you can make parts for oil and gas. This is not a mandatory standard. It is a standard if it is called out in the purchase orders. This is what I mentioned. You have to be aligning your purchase orders to the new requirements. This is a standard that will help if you put it on your purchase order to say the supplier needs to be meeting minimum the APA 20 years requirements conformity. So that's something that will help. And I understand that Wipro is going in for a certificate. This is a standard that you can get a certification, and Wipro is working on that actually. So in this standard, you'll see, like the building standards, you will understand there are essential variables. There is a qualification needed. You'll have an MPS. You'll have levels of different levels of quality. It talks about the first article, production part. It also talks about a lot of things about the non-destructive examination. All these things are covered in this APA 20. So it's a very, very good standard that really, I would say, is a gateway, that it opened a gateway for approving or using additive printed, or considering, I'd not say approving, I would say considering additive printed parts in the oil and gas industry. And ASTM, I think there are multiple standards. I showed you some of the standards references in the previous slides. There are multiple standards of ASTM available. The only thing is that we need to be clear enough what are our standards that needs to be complied with. Those standards needs to be put in place. That need to be on the purchase specifications. That needs to be understood by us, and then also in agreement with the supplier. So for different materials, there are different standards. So what happens is, like, we are familiar in ASTM for different kind of manufacturing processes, but I think there's a lot of learning needs to be done to understand the application of these standards in the additive printing business. ASME, I'm bringing up a code actually here. I think there are multiple different codes, but this is one of the key things where we don't have a full, I would say, ASME is a code that dictates about the different kinds of materials that can be used in a pressure part. So, and ASME Section 8 has to, include these additive printed parts, additive manufacturing process, etc. If that code includes it, then automatically it becomes a process that everybody can start using. However, what they have done now is, if I understand it, what they have done is they come up with a pressure technology book, and it's called ASME PTB 13, and it is about using additive printed parts for the pressure industry, which is the oil and gas, and it talks about dye printed NDE process, dye printed examination is a focus there. It talks about the CT, is promoting the use of a CT actually, which is a computer tomography, which is what we use in the medical industry, and it also talks about the real-time defect monitoring, etc. So what this is going to do is this is going to give a guideline to the code for establishing, material specifications or code requirements, etc. for the future. So I think I was told that 2025 would be the time when ASME would be looking at revising that. So hopefully once that is done, you'll see that more and more components would be printed. And I cannot show it here, but then if you Google up, you will be able to see that that Emerson has already printed a valve body, and that's available on the internet. So you can Google and you can see that they have at least printed a valve body. I'm not sure how much was used, etc. But then it is printed, and as you can see, there are guidelines available here. APA 20 years and the ASTM standards are available, and the PTB 13 is available. So using these guidelines, you certainly can look into printing parts, and of course it needs to be aligned to a customer requirements. It needs to be aligned to a company requirements. Yeah, it's not like tomorrow morning we can go and start manufacturing these parts like that. So that's why I brought this slide specifically up. So this is a key differentiator for the oil and gas industry. If we are, once these standards are up and we are clear about it and the purchasing specifications change, I think the way the industry will be looking at additive printing will be different. Next slide. Again, the process is the last slide. So we are looking at different opportunities. So whatever we have been looking at is about 4-inch, up to 4-inch. But now we are starting to look at larger parts, which is about 6-8 inches. And we are also, as I told you, we are also in the pump industry. So we are looking at some pump parts, impellers, but in the impellers, we need a very special finish. So we're looking at AFM for improving the finish. But we are not started that process, but we are in discussion. We are thinking about it. And I also see some good opportunities with respect to toolings, both foundry tooling and machining tooling. Machining is about the fixtures, etc. If you want a quick fixture, you can get it there. Foundry tooling, both metal and plastic, it's available, and we are actually, a little bit thinking about the use of plastic. It's a very special plastic that Wipro has. So we are thinking about if that can be used in making quick toolings for us for manufacture of casting parts, and where the volumes are not particularly high in those components. Okay, and because again, as I told you, most of our components are engineered parts, so which makes it unique and very low volume but high mix. So we are thinking about that. And another thing is like about there are multiple suppliers who are now coming up with this concept of hybrid, where the sand castings go with the ceramic cores for so they also have capabilities for printing ceramic cores. So we are thinking about that as well. So in general, any component can be manufactured in AM, but I think we need to do a lot of thorough review and multiple modifications to make sure, and also make sure that it meets all the industry requirements and our own company requirements and our customer requirements. I think that's what I have today, and thank you for your listening.